if you are not planning to, learn something about the algebras in future, then I hope that, well, in this lecture series, I hope you can just know a little bit more about the algebras and also Lie groups, like what like sort of their role is in mathematics and physics. If you have taken some like courses, or you are going to take some courses about the algebras or Lie groups, well, you can think of this as a review or preview, and well, I hope there will be some of the things that haven't or will not be covered in maybe the lectures or books. Okay, then almost. But anyhow, so let me just give you the sort of motivation. Right. So from physics, we want to sort of describe the world, nature in a with a rule of like which has a like sort of general validity, and this is gives us the concept of symmetries. So usually these symmetries are described by groups of transformations. And if it's a continuous group, then we can describe this with the underlying algebra. So there is a theorem called Noether's theorem. So I'm not gonna really discuss this in a very precise manner or even derive it. And I just said that it says that a continuous symmetry often gives a conserved quantity. So for example, when we have translational invariance or translational symmetry in our space, we would have conservation of the momentum. So that's the rough idea or basic idea of Noether's theorem. And also there is sort of a quantum version called Ward-Takahashi identity, but I'm not gonna go through the details. So I can give you more examples maybe. So maybe the first one is the so-called Poincare symmetry. So this is the symmetry of flat space-time. And this is given by translations, rotations. And if you take any course in relativity, you will know something called Lorentz boost. If you don't know, you can sort of think this as the rotations with a mixing of space and time. And Wegener's result or theorem said that particles are then characterized by their spins and mass. By their spins and masses. And also, well, in quantum mechanics, usually there is a so-called U1 symmetry on your wave function, which says that the physics does not change with a transformation on the wave function like this, where A is a constant. So we'll have more sort of concrete and explicit examples later when we will mention the application sort of in standard model. So we'll see more sort of symmetries like this. And also there is symmetry breaking. So I also borrowed this example, but it's a quite explicit example. So you have suppose I have a pen or a cylinder sending this on the plane. Then around this z-axis, I have a rotational symmetry because no matter how rotated, it looks the same. But the ground state um, is not invariant under the symmetry. So by ground state, I mean, it's just this state. So your pen just fall on this plane, and now you don't have this sort of rotational symmetry because it would just go like this. So such mechanism, same mechanism, can be found. Well, say in superconductivity and in superfluids, and also the Higgs mechanism. I mean, Higgs mechanism is really say a success of the standard model, but of course we don't have time to go through like every details. But if we have time, we'll mention a little bit about this sort of Higgs mechanism, that how it sort of breaks the symmetry. So much for the motivation. So today I'll talk about the algebras, which is sort of and also the Lie groups. They're almost they're basically ubiquitous in physics as sort of symmetries of the systems, and also I will mention the sort of affine version, and also so-called super versions. But I'll mention them very briefly. So because we only have sort of 3 lectures today, and I'm really gonna start from the very beginning, the definition of the Lie algebras, and then go all the way to sort of its applications, etc. So I can't like cover every details, and I may skip many like sort of proofs, etc. So if you're really interested in this, I will give you some references. So the first one is called Introduction to the Algebras. So this is the book I used when I was learning a Lie algebra course, which is written by Erdmann and Weldon. And also for the affine version, okay, before the affine version, there's also a very standard textbook called Representation Theory by Fulton and and then for the affine version, the first book I read was called Affine Lie Algebras. And Quantum Groups by Fuchs. So if you, so in the first chapter, this book talks about the algebras, and the second chapter introduces the affine algebras, and then in the following chapters, the author talks about these applications, say in conformal field theories, and also mention these quantum groups and Hopf algebra, etc. And of course, if you want a more sort of expanded version, especially for those who are interested in, theoretical physics, you have this book called Conformal Field Theory, which is the sort of Bible in CFT. It's called written by Francesco Martiu and Sinistro. Also, for both mathematicians and physicists, the standard math textbook, there's another one called Infinite Dimensional. The algebras. Okay, I'll just write. Written by Katz. So the Katz-Moody algebra Katz. So, and okay, I'll just go now. So for tube algebras, there are two books I would recommend. One is called Dictionaries. Dictionary on the algebras and superalgebra. So, I mean, of course, you can download it from some websites online, and there is also a shorter version of the book from arXiv with the arXiv number TH 9607161. So it's written, or at least appeared on arXiv in the year of 1996. So it's quite a old book, and it's written by these three people. Another one is a book called The Superalgebras and Enveloping Algebras. This is written by Minsung. So, and also later I'll mention the sort of very simple application on in string theory using sort of the brains, etc., to discuss something called roots in the Lie algebras, and also maybe some sort of like the representation theories, etc. There is a paper called brain. Well, it's over 200 pages, a review paper, so it's almost like a book called Brain Dynamics and Gauge Theory. For those who are interested in, string theory and brain dynamics, written by Eugene and Kutazov. This is you. And it's also on arXiv with the arXiv identifier HapTH 9802067. So appears in 1998. And of course, there are many, many more books on the algebras, because it's really sort of well-developed subject, and some of them standard references you can also see from, I don't know, other books or other courses, and some of them are just sort of might be useful for some of the topics we will mention in this lecture. So yeah, so much about the motivation and the reference. So I want to start with the so first is the definition of the algebra. So first I'll talk about the algebras. Well, of course, definition. So, well, let's just start with the most sort of general definition. Let F be a field. And the algebra, well, let's call it, say, L over the field F is an F vector space. Together with a bilinear map, which is called the Lie bracket, often denoted as this square bracket, which takes a pair of elements in your Lie algebra and sends to this element satisfying the following two conditions. So first, it's antisymmetric. i.e. xy is equal to minus bracket yx. And second, it satisfies the Jacobi identity. Which looks like this. So it's kind of like a collection of brackets in this cyclic order. So that's the okay, and also of course for any x, y, z in your algebra. So that's the definition, and so it's basically a vector space with three ingredients. First, this map, this Lie bracket is bilinear, and then it's antisymmetric and satisfies this so-called Jacobi identity. So there are a few remarks. First, this Lie bracket is often called a commutator for the reason to be cleared shortly. And then today, so we'll mainly take our field F to be the complex numbers. So so shortly we'll maybe later we'll mention something about the real cases, but basically we'll work with the complex numbers. And also, well, I guess we all know what this means, but let me just mention this, what this bilinear what does this bilinear map means? So it just means well, say alpha 1 x1 plus x2 y is equal to alpha 1 x1y plus x2y. For any alpha 1, well, here we just take the field to be complex numbers, so it's C. And this is linear in the first argument, and also it's similar for the second argument. And also, sometimes this being anti-symmetric condition is also written in an equivalent way. So here we just say it's this xy is minus yx, but this is equivalent to the commutator or the Lie bracket of any element with itself is 0. So this is not really hard to see because, well, let's to see this. First, go in this direction. Well, we just take x equal to y, because now we'll have x commutator equals minus x commutator. So it has to be 0. The other direction, so which says our condition says x is 0, so let's write, so it's for any element, so let's just write x plus y, and this is 0. But then, let me write it here. Then this is xx, because it's bilinear, so we have xy, yx, and yy. But these two are 0. And we're done. Because then we're left with the two, which are antisymmetric. So a few examples. Well, first, any vector space. V can be given a Lie algebra structure. With the Lie bracket given by xy being 0 for any xy in your vector space. So this means it's an abelian Lie algebra, because everything the commutator of anything is 0, or we say any element just commutes with any other elements. So for example, the complex number C can be regarded as a one-dimensional abelian Lie algebra. So a slightly more non-trivial example, which is also a very important example, is the so-called general Lie algebra. So which is denoted as, well, because it's called general Lie algebra, so it's denoted as GLV on any vector space, and this is the set of all the linear maps from V to V. And the commutator or the Lie bracket is by, first we take the map y and then compose it with x and minus yx. So that's why it's so that's why the Lie bracket is often referred to as the commutator. In other words, because they are linear maps, so they are matrices, and there is a capital version of GLV. These are the set of all invertible ones, invertible maps. Because they're matrices, so in terms of the matrices, it says the determinant is non-zero for any element in this capital GLV. So, you know, from yeah. So for matrices, we know there are the matrices can be multiplied to have matrix multiplications, but here in the algebra, we only have this thing. So we don't have sort of multiplication defined in the algebra. So maybe more remarks. In other words, the algebras are often non-associative. So this means x, y, z. Well, first I take x, y commutator and then take the Lie bracket with z is not equal to x, y, z. In other words, so in a more, I don't know, familiar notation, so if, well, let's say, let's define an operation called this star product, which is exactly the same as this Lie bracket. One bracket over. Oh, yes. Yeah, thank you. So it's just not equal to x star, y star z. So I mean, sometimes we want an associative version of this Lie algebra, and this is called the universal enveloping algebra of the Lie algebra. Of course, we are not gonna give a rigorous definition of this universal enveloping algebra, but the idea is just to take sort of the formal series, like the products of these elements. So in other words, we do introduce this kind of products in the universal enveloping algebra as long as we impose this condition, saying that this is equivalent to xy. So in other words, we just in this Lie algebra, we further really introduce sort of product of the elements, so we can make it, we can have an associative operation in the usual sense. So like for the matrices here, as a Lie algebra only have this commutator, but now in sort of the associative one, the associative version will have the matrix multiplication, and there is a sort of subalgebra, which I haven't really defined what a subalgebra is, well, but you probably know what that means. So it's called special linear. Algebra, which says so well, again, we'll have x, y equal to xy minus yx. But now we require the trace to be 0 for any x in this SL. And also there is a capital version which says the determinant should be 1 as a subalgebra of GL, capital GL. So this is a subalgebra, so I should define what a Lie subalgebra is. We say K is a Lie subalgebra of our Lie algebra L. If, well, of course, K is a vector subspace of L, and such that xy is also in K for any xy in K. In other words, K is closed under this Lie brackets operation. Well, example is that this is the subalgebra of little GL and C, and also there is a very important example when this SL, little SL and C is with n taken to be 2. So this is, I mean, it's just SL2, okay, so SL2C. And sometimes you can see the notation like this. So for any n, you can write SL like this. And since we're basically working with the complex numbers, so I'll write this as SL2. And there's something called SL2 triple. In other words, because SL2 is basically 2x2 matrices with trace 0, so we can just write all the elements like this. Yeah, for any, of course, ABC complex numbers. So I can just write it as in the basis like this. So it's 1, 0, 0, minus 1 plus C 0, 0, 1, 0. If I call this H and I call this E, this is F, and that's why it's called an SL2 triple, because I have 3 elements, and they will satisfy. If we check the commutator, this is equal to 1, 0, minus 1, which is H. And likewise, HE commutator is 2E, and HF commutator is 2F. Oh, sorry, minus 2F. So in general, if I have a basis, so suppose I have a Lie algebra with basis, so x1 up to, say xk, maybe not k, n, then this would fully determine the Lie algebra because any commutator can be written as the sum over the basis, and these Aijk are called structure constants. And in particular, it suffices just to say determine for just half of the structure constants because AJIK is equal to minus AIJK, since the bracket is antisymmetric. So if you have taken any courses on algebras, then you know we first introduce an algebra, then we talk about subalgebra, then the next object will be ideal. So definition. An ideal of the algebra L is a subspace I of L such that xy is in I for any x in I and y in L. So if you remember from, say, your course on algebras, there is a notion of left ideal and a notion of right ideal. But here it doesn't matter because it's antisymmetric. We'll have the bracket is antisymmetric. So we just need this definition. For example, one can check that the strictly upper triangular matrices is an ideal of the upper triangular matrix. So, and also, one can check that not just SLN is not just a subalgebra, but also an ideal of GLN. Later we'll, yeah. So, okay, maybe there is a 0th example, which is the trivial ideal. 0. I mean, 0 itself, because it's an ideal, because you only have 0. And also, there is something called center of a Lie algebra defined as the collection of all the elements that commute with everything in this Lie algebra. And this is an ideal. So, and in particular, if the center is equal to the Lie algebra itself, this means it is abelian because everything just commutes. So basically, that's all the sort of basic, I don't know, definition and concepts in the algebras, just like what we when we talk about abstract algebras. But the algebra is kind of special because we can classify to some extent the Lie algebras, and this involves something called simple Lie algebras. So because we can sort of, in the end, we can classify them. So I guess that's what's called simple. Okay, I mean, that's not the reason it's called simple, but it turns out it's sort of the simple family of the Lie algebras. So we say a Lie algebra is simple if it has no non-trivial proper let me write it here. Ideals and it is not abelian. So 0, of course, is an ideal. So 0 is always an ideal for any Lie algebra. So that's why we need non-trivial. And proper means it's not the Lie algebra itself, because Lie algebra itself is, of course, an ideal. So that's why it's called no non-trivial proper ideals. And this extra condition for being non-abelian will be clear when we talk about semi-simple Lie algebras, because if we remove this definition, a Lie algebra could be simple but not semi-simple, so which is sort of something we don't want. So and later we'll give a full classification of the simple Lie algebras. And also another important concept is called, well, homomorphisms. So again, definition. So yeah, just to really talk about their applications in physics and string theory, we really need to give all the definitions. So if I have two Lie algebras, say L1 and L2, well, let me just say over C, so we can define this over any field. Then we say a map phi from L1 to L2 is a homomorphism. If, well, first, of course, phi is linear. Phi is a linear map. And second, phi, we say phi preserves the Lie bracket. In other words, phi xy, well, we first take the commutation and then take phi is equal to first take phi on the two elements and then take the Lie bracket for any xy in L1. So there is something quite obvious, but I still want to emphasize a little bit. So here, this bracket is for L1 because it's the bracket on x and y inside the arguments of phi, and this is the bracket on L2. But that's sort of obvious, but I still want just to point it out. And also, if phi is further 1-to-1 and onto, we say it's an isomorphism. So that's the sort of usual definition. A very important example is called the adjoint homomorphism. Which, well, is denoted as AD, which sends L to GL, the general linear L of L, which sends elements to something denoted as add with the subscript X, which is this linear map. Well, because add just sends L, so in other words, this is a linear map on L. So of course, we want to check that this is a homomorphism. Check this is homomorphism. Well, first, it's automatically linear because the bracket is linear. Then we want to check that it preserves the bracket. So we want to show that it preserves this bracket. So first of all, I have this. I've just used this definition. I just have this. Then on the right hand side, I would have this x of z. So this is well, let's just call it left hand side, and this is right hand side. And this again, write it out. Okay, yeah. This is wrong. This is y x minus so they're the same because this is essentially the Jacobi identity. You can check this by yourself, but indeed this is a homomorphism. And another example is something we all know, trace. So it's GLN to C, because C is an abelian Lie algebra. So exercise, check this is a homomorphism. It should be quite straightforward. So two things about this homomorphism and the subalgebra and ideal we've just talked about. So suppose I have a Lie algebra homomorphism called F from a Lie algebra L to another Lie algebra M, then the image of F well, of course, it's this f of x. This is a Lie subalgebra of M. And the other thing, well, it's the kernel of F, which is everything that is sent to 0 under F. This is an ideal. Of L. So how am I doing with time? Okay. Now, okay, I'll just skip the proof of this. So again, this is, I mean, it's really simple. So I mean, as long as you've taken any, like, you know, any algebras, you should be able to do this. So proof, again, exercise. I mean, it's really straightforward. Well, if you don't want to do it, you can just take this as a fact. But then, there is a corollary, which is something we've already mentioned. SLN is an ideal of GLN because trace, okay, the kernel of the trace is SLN. Because trace, but I mean, because SLN by definition is trace 0, so that's kind of like a slightly fancier proof saying that this is a SLN is an ideal. Also, if I have two ideals, then I have the following operations: I intersects with J, I plus J, and I take all the um, commutators, namely the set of xy with x in I and y in J. These are all ideals of L. And we'll have this inclusion. I intersects J, of course, is in I and J, and it can be embedded into I plus J. And of course, everything is in L. So for example, there is something called derived algebra, which is denoted as L primed. This is just taking this bracket L or L and L, and this is an ideal. For example, GLN primed uh, is SLN. And also there is something called quotient algebra, which is basically the same as the quotient algebra uh, in the usual sense. So it's just this for Z in L with the bracket defined as this for any set X in L. If you know, you've done you've seen similar concepts like quotient algebras, then you know you can check that this is a well-defined definition. And there is a sort of important isomorphism theorem called the first isomorphism theorem, which says, so if I have a homomorphism called phi, then L1 quotiented by the kernel phi is isomorphic to the image of phi in L2. For example, GLN quotient by SLN is isomorphic to C. So that's called the first isomorphism theorem. So you know there will be the second and the third isomorphism theorems, but we're not going to use it. So I don't have to mention it here. So there is another concept called solvable Lie algebras, but to introduce that, we first have a lemma which says I have an ideal I of L, then L over I, the quotient algebra is abelian if and only if the derived algebra over there is contained in the ideal. So in other words, L prime is the smallest ideal such that L over L prime is abelian. I mean, this is an exercise if you want to just check this, but so here we've defined this sort of derived algebra, so we can just keep doing this. So why just take like one commutator? I can just keep taking the commutators. So it's called, then this gives me something called the derived series, which, so of course at the first one would just be this L with a superscript bracket 1 is just this. And then for any K, as one may expect, it's just L K minus 1, L K minus 1, taking the brackets. So L2 is just the bracket of this. And of course, LK is an ideal of L because it's just taking brackets of ideals. And we say L is solvable if there exists some positive M such that this is 0. So remember when this is 0, we say L is a billion. So this kind of like an extension of abelian Lie algebras. And also we have a slightly different, okay, maybe let me write it here, just slightly different way to take this sort of series using the brackets called the lower central series, which again, well, L1 is just this L, but LK is this. So for example, L2 is like the superscript K, superscript 2 is this. But L little, subscript K is this one. So we just have the bracket in the second part, etc., etc. And we say L is nilpotent if there exists some M positive such that L lower M is 0. So there is a fact that L solvable if and only if its derived algebra L prime is nilpotent. And in general, nilpotency implies solvability. Well, simply because L superscript M is contained in L subscript M. So with this, we are ready to define the semi-simple Lie algebras. But first, we need to introduce something called the radical of a Lie algebra, which is defined to be this L rad is the maximal solvable ideal of L. So here this maximal means it's not well enclosed in any larger solvable ideal. In other words, there does not exist another ideal J such that L rad is in J, which is in L. So there is, I mean, of course, by definition, L is solvable if and only if L is equal to its radical. So now we can define the semi-simple algebras. So we say L is semi-simple if it satisfies the following equivalent conditions. First, L has no non-zero solvable ideals. Second, the radical of L is 0. Third, L has no abelian ideals. And 4, L can be decomposed as a direct sum of Li's, where these Li's are all simple. So usually in the definition, in any textbook talking about semi-simple algebras, they will list one of, I mean, the first three are sort of, the equivalents are more or less straightforward. The fourth one requires some work. So usually in any of the textbooks, when giving a definition, they would just give one of them, and the other, well, for example, we'll give this one, and the other will be some sort of theorems showing that it's equivalent to being semi-simple. But especially showing that the fourth one is quite non-trivial. So so we just take this everything as a definition and understand that they're all equivalent. So here I've used the direct sum. So I guess I should also define this, like explain what this direct sum means, like in a proper way. So I have two Lie algebras, and then I can define the direct sum as this for L in L and M in M. So for any alpha in C, I should satisfy this scalar multiplication as this. And also, for addition, I have this. This is just L1 plus L2, M1 plus M2. And also the bracket, L1, M1, L2, M2 is given by taking the bracket on the two parts respectively. So the dimension of this would be naturally equal to the dimension of the sum of the two parts. And there is a sort of natural embedding L into L plus M, just given by sending L to L0, and likewise for M embedded into L plus M. So sometimes you'll see something called reductive Lie algebra. it just means L is a direct sum of a semi-simple Lie algebra plus an abelian Lie algebra. So I'll just use S as semi-simple. And it is important because for any Lie algebra, L, it is sort of built of solvable, well, L radical and a semi-simple Lie algebra. In other words, L can be always written as okay. In other words, this semi-simple, we always get a semi-simple Lie algebra when we just quotient this L rad. So that's why we kind of want to know the classification of simple Lie algebras, because simple Lie algebras taking the direct sum gives us the semi-simple one, which sort of builds the Lie algebra together with its radical. But to do this classification, we need something called a Cartan subalgebra. So it's a sometimes just write as CSA. H denoted as H of the Lie algebra L is the one satisfying the three conditions. First, it is abelian. Second, it's something called, the element is called semi-simple for any H in capital H in the Cartan subalgebra, which I'll explain shortly. And there is also, and also it's maximal with respect to the above two properties. So, by the way, there is also called something called the Borel subalgebra. I just want to mention here, but we're not going to use it. But it's something, okay, let's say B of L. It is just a maximal solvable subalgebra of L. So, and to explain the three conditions. So the first one is quite obvious. I mean, it says H is abelian, but this only means H is only within H. So in general, H and X is not zero. Well, for H in the Cartan subalgebra and X, any element in L, except unless X is in the Cartan subalgebra as well. So for the second condition, which says H is semi-simple, yeah, okay, maybe I can give you the original, like the most original definition, which says if we consider the adjoint action of this element, then every this invariant subspace in L has an adjoint action invariant complement. But this is a bit too abstract. So because we're working with an algebraically closed field C, so this simply means the adjoint action as a matrix is diagonalizable. So that's what it means. And means to be semi-simple. And maximal just means that this is the sort of maximal in the usual sense. So if K in L is a subalgebra such that H is in K and K obeys the first two conditions, then H is equal to K. So that's the Cartan subalgebra. Um, so now basically we are ready to sort of give a, list of the all the simple algebras using because there is a sort of root decomposition using this Cartan subalgebra. But before that, I want to talk about representation theory of the algebras because that's when we talk about sort of the algebras, for example, for particles in the standard model or the matters in the world, we just what under some sort of symmetries, we're talking about their representations. So a representation, um, I'll just write as a rep is so of the algebra L is a algebra homomorphism phi, well, L from to the GL for some vector space V, where V is a, well, finite dimensional vector space. Over C because we're working with C. So for brevity, we would often just say that V is a rep instead of mentioning all the homomorphism, etc. And we say it's faithful. The representation is faithful if the kernel is zero. Why is it called faithful? Because we have because I mean when we have a homomorphism from L to GLV, we have this. So usually when we take the representation and working with the image of phi, we would lose some information because there was something contained in this kernel. But if kernel is zero, then basically we lose no information and we say it's faithful. So, well, examples. The 0th example is the trivial representation, which sends everything to zero. And then there is something called, okay, it has different names. Sometimes it's called, well, basically in math literature, well, sometimes it's called natural representation, and sometimes it's called defining representation. And physicists usually call it fundamental representation. So this is just the identity map for L included in GLV. So if L is a, of course, L is a when L is a Lie subalgebra of GLV. Another one is called the adjoint representation. Adjoint representation. So it's just this map which sends X to adjoint X. Basically, that's the homomorphism we mentioned before. And there's another thing called Lie module. So it's essentially the same as a representation, but it's a sort of different way to formalize it for L, or sometimes we just call it an L module, or well, is a finite dimensional vector space. V together with a map L cross V sends to V such that, let me write it. Well, first, it's linear in, so basically sends, well, let's say X little v, okay, and this already smaller, so this is little. Sends to X, denoted at X dot V, equal to lambda X dot V, dot V is equal to lambda X dot V plus mu Y dot V. And of course, also linear in V, so we will have X, it's lambda X dot V plus mu X dot W. And also we have the bracket, which is X dot Y V minus, as the usual commutator. For any mu nu, okay, I use lambda and mu. Lambda mu in C, XY in the Lie algebra, and also little v, little w in the module V. So so as I was saying, they give the representation and the module, they give the same structure. So maybe I should write it down. So reps and modules give the same structure, which can be seen as follows. So given the representation phi from this, we can make V an L module by defining X dot V as phi X acting on V for any X in L and V in V. So if you want to do an exercise, check that this satisfies the three axioms or the three conditions in the definition of the module. And likewise, if so conversely, I have an L module V, then we can regard V as a representation by the following. So we just define phi x to be the linear map that sends V to x dot V. But in other words, so the purpose of mentioning this is that in the following, I'll just use the word representation and modules interchangeably, and they're referring to the same thing. So, and we have, of course, a submodule. So the W, so it is a subspace of the module V. Well, we say it's invariant, which is invariant under the action of L. In other words, x dot W is still in W for any x in L and W in W. So, and also we can likewise define the quotient, which is basically, okay, let me just write it here. Quotient is just basically x dot V plus W, V plus W. Well, this W is a submodule of V. So, and also we have, if we have two modules, say U and V, they're both L modules, then we say the map theta from U to V is a homomorphism or an L module homomorphism. If theta x dot U is equal to x dot theta of U. Again, for any x in L and U in capital U. So basically, we're just doing the similar stuff when we talk about when we were introducing the Lie algebras. And then there is something called irreducible module, irreducible representation. V, well, first, of course, we don't want it to be trivial, so if it is non-zero. And it has no submodules. And of course, other than, 0 and V itself. So sometimes we just say this is the irrep, means irreducible representation. And also there is a, we say it is indecomposable, composable, if there does not exist any non-zero submodules, say U and W, such that V is a direct sum of U plus W. So later we'll also classify the representations for the Lie algebras and the Lie groups, because we'll see that there are, when we introduce Lie groups, the representations are actually in one-to-one correspondence. So at least for a family of the Lie algebras and Lie groups, will classify the representations, and at that time it will be much more, well, I'm not sure if it would be much more interesting, but at least we'll have some pictures rather than just giving you all the list of definitions. So, but now let's just do one example, which is sort of more concrete, which is the representation theory of SL2. So that's basically our sort of prototypical example. Well, first let's introduce the polynomial ring, which is the polynomials in x and y with cost complex coefficients. So for example, x is a polynomial, xy is a polynomial, y squared is a polynomial, etc., etc. And let's define a subspace V of D, B sub D, which are the polynomials, and of course in this CXY, such that the degree of the polynomial P is D. So this is in V1, this is in V2, this is in V2, etc. So now I want to make a claim. VD is a representation of SL2. Remember, we talked about this SL2 triple, so it suffices to consider EFH because that's they span the whole SL2 with the Lie brackets we've just seen before. So now the representation is given by phi of E is x d over dy, and phi of f is y d over dx, and phi of h is x d over dx minus y d over dy. So notice that phi of h x, well, diagonally. Okay, maybe I shouldn't write this, but just give you the expression. So for any polynomial xa, y, and to the power b, we find this is just a minus b, x to the a, y to the b. So this will mean by x diagonally. So in other words, when you x phi of h on this d, it just gives you you just stays in this vector space. And if you xe, it would lower the power of y by 1 and increase the power of x by 1, and vice versa for phi of f. So we can finally have the sort of first picture today, which is this. So I start from 0, then I have the space spanned by y to the power d, then I have xy d minus 1. Then of course I can just keep going. X, y, d to the minus 2, etc. Then I have x d minus 1y, x d. Then I'll go back to 0 because if I act to h, well, h is still, itself, so it doesn't mean anything. But I can have f acting on it because maybe that's the other way. Okay. Yeah, f acting on it because it has no x, so it will give me 0. So it sends the space given by yd to 0, and likewise, f just takes me from the right, the point on the right to its left neighbor. And what E does is the opposite direction. And also H just stays here. Everything just stays in H. So in fact, we can even use a different pictorial way to represent VD. So VD is in one-to-one correspondence with an array of boxes. So in other words, we just write it as a box of length D, which encodes the, encodes the length of, the powers, the degrees of the polynomial. It's sort of I don't know, redundant thing to do. But later when we generalize SL2 to any SLN, we'll see they are given by something called Young tableau, which is basically like more boxes below. So they are actually in one-to-one correspondence with the representations of SLN. And in fact, okay, let me just call this theorem. First VD is irrep.
What is the phi, and because they're just element of the representation.
Which one?
Phi E, phi alpha.
Yeah. So it's representation of E. Yeah. So because EFH fully determines the SL2, so I just need to write out these three. But yeah. So yeah, and also if V is of course a finite dimensional rep of SL2, then V is isomorphic to one of the VDs. In other words, VD fully classifies the representation of SL2. And I guess I should stop here. So yeah. So I haven't really finished the discussions on the algebras, and there were some, well, the next thing is just to classify all the Lie algebras. But that's kind of a very important thing. And then we'll talk about Lie groups and see why they're both given the name Lie due to the mathematician Sophus Lie. But and then after talking about Lie groups, we can finally discuss some sort of applications, etc. So yeah, I guess I'll stop here.